Hello, we are presenting a report on data pre-processing and preliminary analysis of crop production. This data basically refers to the district-wise, crop-wise, season-wise and the year-wise data on the crop, covered area and production. The data is being used to study and analyze crop production, production contribution to different district, state or country, agroclimatic zone-wise performance and high yield production, order for crops, crop growing pattern, and diversification. These are the contributors. It was released under National Data Sharing and Accessibility Policy. These are the contributors, and these are the sector is agriculture. The source was data.gov.in. These are some of the questions of preliminary analysis that will be answered in the inference. Now the data description. This is the size of our data, which is 2,46,091 rows and 7 columns. The dimensionality, which is basically the number of features, it is 7. The feature description. The features here of the data set are state name, district name, crop year, season, crop area and production. The nominal attributes are state, district, crop, season and crop year, season and crop. Nominal are basically the categorical values. Here then we have the interval attributes. These are area and production. These are the continuous attributes that for which the difference matters but the ratio doesn't matters. The independent features we have are state, district, crop year, season, crop and area. These are independent because the dependent feature, that is production, it depends on all of these. Now data quality. First, noise. We have seen no overlapping in the graphs, that no instance overlaps the other instance, so there is no such extraneous object, and so we have no noises present in the data. Then we have the outliers. The outliers, they are observed below in the box plot that is explained later in the documentation. Then for the missing values, there are 3,730 missing values in the production column, and other than that there is no missing values. These missing values are handled in the pre-processing section. Then for the duplicate data, there are no duplicate rows present in the data set. Now data pre-processing. First of all, we have imported libraries. First, pandas, which are used to convert the CSV files into the pandas data frame. Then we have numpy, that is used for handling the arrays. Then for the graphs plotting, we have seaborn and matplot, and the further pre-processing functions will be explained later. Now first we have imported the database here. These are some of the instances of it. Then determining the size of the data set. This is the size of the data set. Then these are the features of the data set. Now here we have divided the data set into independent and dependent features, and then converted into arrays by the ilog function.
Now we'll see how to remove the missing values. First of all, we're calculating the missing values through this function. We get 3730 missing values. Now, how we replace the missing value is, first of all, we replace the empty value with NaN. Next, to remove them, we group the production state-wise and crop-wise, and then take the mean of the production through that grouping. We replace the NaN with that mean of the corresponding crop and state. For that, we first of all make a new data set of the NaN production. Secondly, we convert this to an array and then group them by state and crop and calculate the mean of the production. We copy this production in the array that we had created, and finally we copy them to the data frame, to our original data frame, that was Pro, that we had created. This is the code that we had used to merge the data in the main data set. So finally we get zero missing values.
Now, when we have seen for the duplicate values by the duplicated function, we have seen that no duplicate values are present here, so nothing is there to remove. Then by the help of describe function, we are finding the measures of central tendency. These are the measures of central tendency. Then the categorical values. Now we need to encode the categorical values because machine learning algorithms, they are based on mathematical equations. So the categorical data are important to handle by encoding them into numerical values. So these are the categorical values, and by the help of the label encoder function from the pre-processing library, we have converted all of the categorical values into the numerical values. These are the numerical values. Now here the problem of comparison arises, as if there are 32 states, so if there are 32 states, so every state is given one number from 1 to 32, and during some of the calculation there may be comparison that one state is greater than the other. So to avoid such confusions, we introduce dummy variables here. The dummy variables here will make a separate column for all the instances of the categorical values, and by the help of zeros and ones, they will show the presence or absence of that instance in that particular row. Then this is the dummy size of the dummy, the newly made dummy column. Then these are the dummy column values. Now, for the further ML processing and the prediction and such stuff, we are splitting the dataset into training and testing sets. This is used by train test split from the model selection library. Xtrain, Xtest, Ytrain, Ytest. These are the for training, the dependent and independent variables divided into the training and testing section. And now further feature scaling.
The last step of preprocessing is feature scaling. For the feature scaling, we use the function standard scaler of the library sklearn.preprocessing. Feature scaling is the method to limit the range of variables so that they can be compared on common grounds. So the range that is commonly used by standard scaler is -1 to 1. Finally, we come to inferences. So for inferences, we have plotted graphs by using the dataset and drawn the inferences. Here the inferences drawn are based on the dataset acquired before removing the categorical values and applying feature scaling for the ease of computation. First of all, we have computed the pie chart. We have drawn the pie chart. For that, we have used the function plt.pie, and we have drawn the pie chart for area distribution of different crops in Karnataka in 2014. So this is the pie chart drawn, and we can infer that in the year 2014, for example, in the year 2014, Karnataka had the maximum area under the crop maize, with the area being 11.95%. So this is used to estimate the area of different crops in Karnataka. Similarly, the graph drawn for Kerala in 2010. Next, we have the box plot. Here, the box plot is drawn for year-wise production in different seasons of Punjab. We can infer from the box plot. We have used the function sns.boxplot, and we have segregated it using the different seasons. So from the box plot plots all the entries, and then is helpful in estimating the mean, median, and the interquartile range. We can also figure out some outliers in this case, which are marked in red color, but we'll not disturb the outliers to avoid bringing variation in the calculation done, as due to any natural calamity, the production can vary significantly, resulting in outliers. Hence, they are justified in this case. Similarly, the box plot drawn for the state of Haryana, where we can see that the production of different seasons is equal in almost all the years except the year 2012, where the production decreased drastically. Now we come to the next graph. This graph tells us how the total production, what is the total production of different crops in a particular state. So for instance, in Gujarat, sugarcane has the highest production over the 10 years. So this is helpful in for the farmers to produce that crop particularly more. Similarly, we have for Chhattisgarh, there is the highest production of rice. For this, we use bar plots and group by the sum the production by grouping crop. Now we have our next graph as the line graph, and this is the grouped line graph. This basically tells us how what is the growth trend of a particular crop in this state. Like for example, in Haryana, we have the production of sugarcane, rice, sugarcane, cotton, and wheat. So from this graph, we can infer that from 2006 to 2008, the production of sugarcane decreased drastically, and the production of wheat increases. Similarly, in Punjab also we can infer these conclusions. Also, we can infer that the production of sugarcane in Haryana is more than the production of sugarcane in Punjab. Also, the similar conclusions can be drawn from this graph. This graph tells us how what is the total production of rice year-wise in a particular state. So in West Bengal, for instance, we can infer that production of rice increases from 2010 to 2014. So these are some of the conclusions we plotted from our graphs. The similar conclusions, more of the conclusions can be drawn, and we can infer which crop is to be produced more and which crop is to be produced less. Also, we can apply machine learning algorithms in this, but we have done the preliminary analysis. For the machine learning, we'll predict the production on the basis of these independent variables. Thank you.